Okay, so this is 11.10. We're going to start with example 13 because it's where we left off. So this is just kind of finishing the last few examples that we didn't get to during the lesson during class. So in number 12, we learned that we could go ahead and write the first three non-zero terms of two things that were being multiplied together, where both of the two things were non-polynomial functions. So it was e to the x and cosine of x, or e to the x and sine of x, one of the two. I can't remember what it was. But because those two were not polynomial functions, you can't take one series and just kind of distribute it into the other one like we could with the x times cosine of x problem. Example 13, pretty much the same idea. We want to find the first three non-zero terms for the Maclaurin series of tangent of x. Now, you could develop this by hand. You could figure out, obviously, that you could do tangent of x is f of x, and then you could do the derivative of tangent of x, which is secant squared. After that, the derivatives are going to become chain rules and product rules and all kinds of other messy things. Since we're only looking for the first three non-zero terms, we can think of tangent of x as being sine over cosine. So tangent of x is the same thing as sine of x over cosine of x. And we already have the series expansions for sine of x and cosine of x. Okay, these are the ones that we kind of should know. So sine is going to be negative 1 to the n. And again, it's the odd term, so it's x to the 2n plus 1 over 2n plus 1 factorial. And if we write out the first so many terms, I'm not going to walk through the entire process, but you would get x minus 1/6 x cubed plus 1 over 120 x to the 5th minus, and so on. Cosine, well, it's pretty much the same thing. And again, you could develop this by taking the derivative of sine, or if you just happen to remember it's all of the even terms, it's going to be x to the 2n over 2n factorial, however you want to do that. So then cosine is going to end up being 1 minus 1/2 x squared plus, what is that going to be? 1 over 20? No, 1 over 24. Yeah, factorials, duh. 1 over 24 x to the 4th minus, and so on. Okay, and I'm just getting that by plugging in 0, 1, 2, and so on. That's how we're getting those values. So the unfortunate part about this is the only way to do this, because again, these are infinite polynomials, is to do long division. So we'll set up our division bar. So it's sine divided by cosine, which means that the cosine part goes on the outside, sine goes on the inside. So it's going to be x minus 1/6 x cubed plus 1 over 120 x to the 5th, and so on. And the good news is we won't need to go any further than that. And on the outside, we're going to have 1 minus 1/2 x squared plus 1 over 24 x to the 4th, dot, dot, dot. And you might actually think to yourself, well, wait a minute, when we did long division before, we had to do this in descending order. Well, think about it. This is infinite. These things are going to keep getting bigger and bigger as far as the exponents, the further and further we go to the right. There's no way to write this in completely descending order. And we don't need to have every single term in between, because what we're going to get when we multiply will fit. If it didn't fit, then we would need the in-between terms, but you'll see what I mean by it'll fit. So what do I need to multiply by 1 to get x? Well, that's just x. So I'm going to line that up on top of my x, distribute the x to everything on the outside, so that's going to be x minus 1/2 x cubed, you see how that lines up, plus 1 over 24 x to the 5th, and that lines up. And then, of course, it would keep going, but we only need these terms because we're only looking for the first three non-zero terms. So we'll subtract. X minus x goes away. Negative 1/6 plus a half is going to simplify to a third x cubed. And then 1 over 120 minus 1 over 24. So the common denominator there is 120, and you should realize these are going to be common denominators because 24 is the step, that's 4 factorial, 120 is 5 factorial. So if I multiply 24 times 5, it gives me the 120. So really that's going to be 1 over 120 minus 5 over 120, which is going to give you negative 4 over 120. Let's write this out. Negative 4 over 120 reduces to negative 1 over 30. Negative 1 over 30 x to the fifth. Now, normally you would go ahead and bring down the next term, but again, we don't need to worry about that because we're only concerned with the first 3 non-zero terms. So now let's figure out what the next one's going to be. What do I multiply times 1 to give me 1/3 x cubed? Well, that would be 1/3 x cubed. So let's go ahead and write that up here. So plus 1/3 x cubed. Distribute that. 1/3 x cubed is going to go here. 1/3 x cubed times 1/2 x squared is going to be minus. It's going to be 1/6 x to the fifth. And again, I don't need to worry about the term after this because it's not going to mean anything. So we'll subtract. The first term has to go away, and it does. So then we're going to get negative 1/30 plus 1/6. 1/6 in terms of 30ths is 5/6. So negative 1 over 30 plus 5/6 is going to be 4 over 30. And that's going to reduce to 2 over 15. So we should get 2 over 15 x to the fifth. Again, don't need to bring anything else down. What do I multiply times 1 to get 2 over 15 x to the fifth? I get 2 over 15 x to the fifth. So these are the first 3 non-zero terms of tangent of x. And again, you could have tried to develop that. It would have been a real pain to develop it the other way. Believe it or not, this was probably the easier way to do it. All right, next 2 examples, and these are the last 2 that we'll get to. Should not be quite as involved. We want to evaluate the integral of x cosine of x cubed dx. Okay, you may or may not remember, it's been a while, but a long time ago I said that there are going to be integrals that we just can't do by hand. And you're going to have to use something that we're going to do at the end of the year. Well, this is that thing. We cannot do this one by hand. X times cosine of x cubed, you can't do u substitution. You'd still end up with an x squared in the denominator that you can't get rid of. So the only way to do this one is to create an infinite series and then do it that way. So what we need to build is our integrand, x cosine of x cubed. So let's start off with the fact that we know cosine of x. Cosine of x is the sum of negative 1 to the n, x to the 2n over 2n factorial. Cosine of x cubed is going to be replacing the x with an x cubed. So we get the sum as n goes from 0 to infinity, negative 1 to the n. If I put an x cubed in there, I'm going to get x cubed to the 2n. Multiplying those exponents, I get x to the 6n. Again, 2n factorial doesn't change. There was no x's down there to plug anything into. Then I need to multiply it by x so that I get the full integrand. And x itself is a polynomial, so we can distribute that into the sum. So multiplying the x to the 6n times x is going to give me x to the 6n plus 1 over 2n factorial. And then if we want to go ahead and find the integral, because that's what we're looking for, The integral of this means we take the integral of that. To be completely accurate, let's put a dx on the end. So then my integral is going to equal some constant plus some as n goes from 0 to infinity, negative 1 to the n, raise the exponent by 1, x to the 6n plus 2, divide by the new exponent, 6n plus 2, important to keep that in parentheses, and then 2n factorial is still down there. And that is the indefinite integral for x cosine of x cubed. Okay, really, that is the only method that we have to be able to do that one right now. Okay, one more example. And then everything after this is the applications, which is going to be covered in our 11.11 section. All right, so if f is a function such that f prime is defined as sine of x squared, find the coefficient of the x to the 7th term in the Taylor series for f of x about x equals 0. So again, it says Taylor series about x equals 0. It's a Maclaurin series, but it's still defined the same way. So the center is 0. We want to find the coefficient of the x to the 7th term for f of x. They didn't give us f, they gave us f prime. Okay, and that means we're going to eventually have to get back to f of x. Taking the antiderivative of sine of x squared, again, is not an easy thing to do by hand. So we're going to create a power series. So let's start off with, well, we know what the power series for sine of x is. N equals 0 to infinity, negative 1 to the n of x to the 2n plus 1 over 2n plus 1 factorial. But I don't want sine of x, I want sine of x squared. So let's build that in there. So I'm going to replace the x with x squared. So if I replace x with x squared, it's going to be x squared to the 2n plus 1. So we'll multiply the exponents together. We're going to get x to the 4n plus 2 over 2n plus 1 factorial. But that's f prime. If I want f of x, I have to take the antiderivative. So our antiderivative here is going to be some constant plus some 0 to infinity, negative 1 to the n, add 1 to the exponent, x to the 4n plus 3 over 4n plus 3 times 2n plus 1 factorial. And I am specifically looking for the coefficient of the x to the 7th term. In order to get this to be x to the 7th, I would have to plug in n equals 1. So for n equals 1, the coefficient is going to be defined by what I get when I plug 1 in for all my n. So it's going to be negative 1 to the first power, x to the 7th, over, let's see, plugging a 1 into the denominator is going to give me 7 times, it's going to be 2 plus 1, 3 factorial, which is 6. So that's going to be the same thing as negative 1 over 42, x to the 7th. So the coefficient, we can say c sub 7, coefficient, is going to be negative 1 over 42. All right, and that should be it. Okay, kept it to under 15 minutes. Go me.